A $1,000 motor lasting 1.2 million miles? Gas engines die at 200,000. Most EVs tap out around 500,000. But Tesla's Model 2 just tripled that for less than an iPhone. The secret? A 0.1 nanometer carbon graphene wrap around the rotor, creating 10,000 megapascal strength, 40% stronger than standard carbon. No rare earths, just one moving part, spinning at 25,000 RPM while staying at only 110 degrees Celsius. But here's what doesn't add up. Why is this motor 60% cheaper than conventional EV motors? Where's Tesla hiding the real cost? Every motor in existence hits the same wall at 16,000 RPM. Metal expands, heat warps rotors, bearings scream, then everything explodes. It's not a design flaw, it's physics catching up with ambition. 4 years ago, Tesla wrapped a 0.5 millimeter carbon fiber sleeve around the Model S Plaid's rotor and pushed it to 20,000 RPM. That sleeve had 7,000 megapascal tensile strength, 5 times stronger than steel. The industry called it a vanity project, a $110,000 supercar trick that would never touch a regular person's driveway. They miscalculated badly. Fast forward to 2025. Tesla's upgraded to a carbon graphene hybrid composite, layering 0.1 nanometer graphene into the carbon matrix. Tensile strength hits 10,000 megapascals, 40% stronger than the Plaid's wrap. The rotor spins at 25,000 RPM like it's out for a Sunday drive. But forget the numbers for a second. What matters is this. They figured out how to mass produce what used to be aerospace-only technology. That's the difference between a science experiment and a revolution. Think about how your phone heats up when you're watching videos for too long. Now imagine that happening inside your car's motor while you're driving. A Model S motor spinning hard for 30 minutes hits 180 degrees Celsius. That's hot enough to boil water. All that heat, it's your battery burning money. Roughly 10% of your charge vanishes into thermal waste. Your range drops, your electricity bill climbs. You're paying to overheat a motor instead of getting where you need to go. Tesla's new graphene layer conducts heat 5 times faster than standard carbon fiber. Same aggressive driving, but the Model 2's motor stays at 110 degrees Celsius. That 70-degree drop isn't just impressive engineering, it's money back in your pocket. The cheaper car runs cooler and more efficiently than the flagship. That's not how cars are supposed to work. Usually you pay more to get more. Here you're paying less and getting better efficiency. It feels backward until you realize what's actually happening. The weight tells another story most people miss. Dropping from 45 kilograms to 38 kilograms doesn't sound dramatic until you're cruising on the highway. The Model 2 needs only 11 kilowatts to maintain 68 miles per hour. The Model S needs 15 kilowatts for the same speed. You're using 27% less power for the exact same result. Every mile stretches further. Every charging session lasts longer. Tesla claims 99.7% energy conversion efficiency. Most EVs struggle past 80%. If those numbers survive real-world testing, this isn't just a good motor. It's rewriting what's physically possible in a production vehicle. But here's where things get uncomfortable for the entire industry. For decades, every EV motor depended on rare earth magnets, neodymium, dysprosium, terbium, exotic elements that cost $100 to $300 per kilogram. They work beautifully. They're also a geopolitical nightmare. China controls 90% of global supply. One export restriction, one trade dispute, and the price of your EV doubles overnight. It's not paranoia. It's happened with other critical materials before. Elon Musk looked at that fragile supply chain and walked away from it entirely. Tesla switched to ferrite magnets, iron oxide and clay. Materials so common they're practically dirt. Literally. The cost drops from $300 per kilogram to barely $5. That's not a discount. That's a complete demolition of the cost structure. Critics jumped immediately. Ferrite magnets are weaker. You'll lose power. The car won't perform. And they were right if you're building a traditional motor. Tesla wasn't. The carbon graphene wrap lets the rotor spin 25% faster, compensating for the weaker magnets through sheer RPM. Same power output, fraction of the cost. It's the kind of lateral thinking that makes competitors uncomfortable because it works. That decision alone dropped motor costs from $2,500 to $3,000 down to around $1,700 to $1,900 on the Model S. Still too expensive for a mass-market car. Still out of reach for most families. Then came the move nobody anticipated. Virgin carbon fiber costs $25 to $40 per kilogram. It's expensive because making it from scratch requires intense heat and precision. But recycled carbon fiber from old aircraft parts, retired wind turbine blades, scrapped industrial equipment, that runs $8 to $15 per kilogram. Tesla waited until the aerospace industry had enough end-of-life carbon components piling up, then built relationships with recyclers. Suddenly, they're cutting raw material costs by 40%. Another $400 to $500 saved per motor. The timing wasn't luck. It was patience. Now pair that with Gigafactory Texas and Nevada running 99% robotized assembly lines. AI-controlled systems integrate stators with defect rates below 0.01%. When you're making 2 million motors a year, that quality leap eliminates warranty nightmares and rework costs. At full scale, Tesla's projections hit $850 to $950 per motor, a $1,000 motor outperforming $3,000 competitors. Ford can't copy this. GM can't copy this. They buy motors from suppliers. They can't redesign factories around a single component. They're trapped by decisions made decades ago. Now let's talk about the durability claim, because 1.2 million miles sounds like someone's exaggerating at a bar. Gas engines tap out around 150,000 to 250,000 miles because they've got hundreds of parts grinding together. Pistons, valves, crankshafts, metal scraping against metal, generating heat and friction until something gives up. Standard EV motors push 300,000 to 500,000 miles with far fewer moving parts. Better, but heat still warps rotors and vibration damages magnets over time. Tesla's carbon wrap motor has one main moving part, the rotor, and a handful of bearings. That's 90% fewer failure points than a gas engine. The carbon graphene wrap eliminates the vibration and thermal expansion that usually kills motors. If Tesla's engineering holds up, this motor could genuinely outlive the car it's installed in. Maybe even outlive you. The maintenance schedule backs up that confidence. Check inverter coolant and clean bearings every 100,000 to 150,000 miles. That's once every 5 or 6 years for most drivers. Each session costs $50 to $70. Over a decade, you're looking at maybe $1,500 total. Compare that to the $5,000 to $10,000 you dump into keeping a gas car running. It's not even close. But there's something strange here. If this motor genuinely lasts 1.2 million miles, 80 years of normal driving, who's buying replacements? Tesla just eliminated their own spare parts business. Unless that's not the real plan. You'll own the motor forever, but premium features, performance modes, battery upgrades, those might hide behind software subscriptions. It's speculative, but it fits how Tesla thinks. Step back and look at the industry impact. If Tesla produces 2 million motors annually at $950 each, that's $1.9 billion in motor costs. Ford, GM, Volkswagen are paying suppliers $2,500 to $3,000 per motor. At 2 million units, they're spending $5 to $6 billion. Tesla just grabbed a $3 to $4 billion annual advantage on one component. Add the Model 2's $15,000 price tag, 370 to 380 miles of range, 0 to 60 in under 3.5 seconds, and a motor that outlasts everything else on the road. What gas car competes with that? What EV offers better value? This isn't competition. It's a reckoning. But one question keeps nagging. If this technology's been proven in the Model S Plaid since 2021, why wait 4 years to bring it to the Model 2? Were they waiting for battery tech to catch up? Was this a strategic delay? Let competitors assume carbon wraps can't scale, then blindside them with a $1,000 motor? Because if Tesla's been sitting on this capability, what else haven't they shown us yet? So where's Tesla hiding the real cost? They're not. They eliminated rare earth magnets, virgin carbon fiber, and supplier markups, replacing them with ferrite, recycled materials, in vertical integration. The 4-year wait was preparation, not hesitation. They needed recycled carbon supply chains mature, gigafactory automation at full scale, and aluminum-ion batteries ready. This motor forces every automaker to rethink their cost structures. If the Model 2 executes at $15,000 with this performance, everything more expensive must justify why. Tesla's already testing next-gen materials for Cybertruck and Semi. What happens when this scales to vehicles running 24/7? My question for you, what breaks first? Legacy automakers adapting or consumers realizing they've been overpaying? Drop your answer in the comments below. If this analysis gave you clarity on Tesla's Model 2 strategy, smash that like button. Subscribe to Tesla Zone and hit the notification bell so you never miss our deep dives into automotive innovation. The future's already here, spinning at 25,000 RPM. Traditional assembly lines just became obsolete. Tesla unveiled a 50,000-ton monster that builds a complete car every 5 seconds, moving so fast that human workers literally cannot get close to the production line. This beast casts 5 Cybercab chassis simultaneously, capable of pumping out 7 million vehicles per year from one facility. Think about that for a second. What happens to Ford, GM, and every legacy automaker still welding 200 parts together when Tesla's already building complete cars faster than you can read this sentence? To understand why this 50,000-ton machine represents such a leap, we need to go back to 2020. When Tesla first introduced the 6,000-ton gigapress for Model Y production, the automotive world dismissed it as a risky experiment. Traditional manufacturers had spent a century perfecting stamping and welding. Tesla wanted to cast entire sections in one piece, replacing 70 individual parts with a single aluminum component. The skeptics had valid concerns about defects and investment costs, but Tesla proved them wrong. Production time dropped, quality improved, structural rigidity increased. What happened next reveals everything about Tesla's strategic thinking. While competitors rushed to order their own casting machines, GM, Hyundai, Volvo all jumped in, Tesla was already engineering something that would make those competitor investments obsolete before the machines even arrived. The 50,000-ton gigapress stands roughly 20 meters long and 12 to 15 meters tall, weighing over 3,000 tons. The foundation requires several meters of reinforced concrete just to handle the operational forces. This machine generates 8.3 times more pressing force than the 6,000-ton model. But raw power means nothing without precision, and that's where Tesla's real advantage lies. The process begins with melting aluminum at 850 degrees Celsius. But Tesla doesn't just melt and pour. They developed a 2-furnace system where the second furnace maintains molten aluminum between 750 to 850 degrees Celsius, with nitrogen gas filling the empty space to prevent oxide formation. Operators use argon gas, rotary degassers, and silicon carbide filters to remove particles larger than 25 microns. At these speeds and pressures, even microscopic impurities cause catastrophic failures. Before each cycle, a robot sprays exactly 35 milliliters of soybean oil across the mold. Too much creates defects. Too little causes sticking. The system creates a vacuum, eliminating all air before a high-speed piston injects the liquid metal under immense pressure. The molten aluminum flows through the massive mold, filling every microscopic detail before cooling begins. Inject too fast and air bubbles form, too slow and the aluminum solidifies before filling the mold. This delicate balance happens at 800 degrees Celsius under thousands of tons of pressure in mere seconds. After injection, the casting ejects at 400 degrees Celsius and plunges into a cooling bath, dropping the temperature to 50 degrees Celsius. This rapid cooling enhances material properties and eliminates defects. The mold cools to 185 degrees Celsius, gets cleaned, and prepares for the next cycle in just